Well, if you've looked through lecture 3.3 called Counting Rules, you know that the first half of it is devoted to yet one more review of the addition rule, the multiplication rule, the idea of complements, the idea of probabilities associated with at least. And you'll get even more exposure to that as we go into the mastery section. But the very tail end of the counting rules is actually the counting rules. And I have mixed feelings about this material because OpenStax did not include it in the text. And frankly, if what you were trying to do is to strip away everything that's just not essential to statistics, yeah, you might indeed take this, what I would call combinatorics. You might take that topic out. Still, it's generally there. It's essential to probability. And it really does help you count, and I think you've seen how important that is, because classical probability is just the number of outcomes in an event that you care about divided by the number of outcomes in the sample space. So if you can count the number of outcomes in the sample space and the number of outcomes in the event in question, you divide one of the other, and lo and behold, you've calculated a probability of occurrence. So counting is everything, and maybe you're beginning to get an appreciation that sometimes it becomes a little bit tricky. So let's look at these first three definitions. The top one is called the fundamental counting rule, and let me just read it here. It says, in a sequence of n events in which the first one has k1 possibilities, the second one has k2, and so forth, the total number of possibilities is just the product of k1 times k2 times k3 ... up to kn. That's also called the multiplication of choices. Okay, now that's actually something that I think you probably have an intrinsic feeling for. These next two definitions are actually what I want to hold you responsible for, rather than the whole totality of this material. I want you to know what a permutation is, and I want you to know what a combination is, how they're different, and how you calculate them. You can use your calculator to calculate them. So let's move through some of these view graphs to start to appreciate what they are. Permutations are rearrangements. Combinations, different sequences of the same items not count, are also rearrangements in a manner of speaking. So back to the counting rule, here's an example. It says a paint manufacturer wishes to manufacture several different paints. They include a color, and there's 1, 2, 3, 4, 5, 6, 7 colors. A type, latex or oil, 2 types. A texture, flat, semi-gloss, high gloss, 3 textures. A use, indoor, outdoor paint. So how many different paints are there? 7 colors, 2 types, 3 textures, 2 different uses, applications, indoor, outdoor. Multiply those all together. There are 84 different types of paint. If by type you mean you have to specify a color, a type, a texture, and an outdoor use. That is making use of the fundamental counting rules. Now, sometimes it's difficult to count how many elements there are in each one of those, how many colors there are, how many types, how many textures. And that's what the rest of this material is about. And this next view graph covers what is called the counting rules. Notice that the first one is the fundamental rule of counting. The next one is pretty interesting. It's called the factorial rule. And it says n factorial has a notation, n, exclamation point. And it's equal to n times n minus 1 times n minus 2 ... times 3 times 2 times 1. So as an example, 5 factorial is 5 times 4 times 3 times 2 times 1. 1 times 2 is 2, 2 times 3 is 6, 6 times 4 is 24, 5 times 24 is 120, 5 factorial is 120. It's really just a shorthand for these rules that are coming up, and you'll understand that in just a second. Oh, by the way, 1 factorial and 0 factorial, they're both 1 by definition. Don't ask, just believe. And why is this important? Because it's the number, n factorial is the number of ways that you can rearrange or permute in different objects. I've got a calculator. I've got a calculator. I've got a case of glasses. 3 objects. There's one rearrangement. This guy's first, this guy's second, this guy's third. Here's a second rearrangement. Here's a third rearrangement. How many of those, how many permutations of these 3 objects are there? Well, a very useful way to think about that is if you've got 3 positions for these 3 objects, there's 3 ways that I can fill this first slot. Let's say I fill it with this calculator. There remains then 2 ways that I can fill the second slot, and 1 way to fill that slot. By the fundamental counting rule, there's 3 times 2 times 1. Or, using this notation, there's n factorial. So if all you're looking for is rearrangements, then n factorial gives you that number of rearrangements, providing all these objects are different. All right? So the permutation rule says, suppose you don't want to take 3 objects and rearrange them, but you want to take 4 objects. Here's my 4th object. But you only want to rearrange 3 of them. All right? Well, then how many different ways can I fill that first slot? Well, I've got 1, 2, 3, 4 different ways that I can fill that first slot. How do I fill the second slot? I'll have 3 objects left. How do I fill the last slot? I'll have 2 objects left. 4 times 3 times 2. You can write that in terms of this factorial notation as the way you read this is n things, the permutations are of n things taken r at a time. N factorial over what's called the difference factorial, n minus r factorial. So I've given you an example here. The example says if you want to take 3 things, if you want to find the permutations of 3 things, 3 at a time, then n is 3, r is 3. Then it is 3 factorial divided by the difference factorial, 3 minus 3 or 0 factorial. 3 factorial is 3 times 2 times 1, 6. 0 factorial by definition is 1. The answer is there's 6. And if you want to think of those objects as the letters A, B, and C, then there are the 6 rearrangements of A, B, and C just below you. So there's the first of 2 permutation rules for number of different rearrangements of n different objects selected r at a time. Here's the second one. Here's the second one when some of the objects are alike. So this second permutation rule says this is the formula for the number of different rearrangements or permutations of n objects when n1 are alike or n2 are alike or nk are alike. The best way I can show you this is to look at this example. Look at the word bookkeeper. It's a pretty special word, right? It's got double O, double K, double E, and then another E thrown in at the end. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 letters. How many rearrangements of that word can you make? Well, rearrangements of 10 objects is just 10 factorial. A big number, by the way, over 3 million. But in this case, there are 2 of those objects, the O's, that are identical. There are 2 K's that are identical. There are 3 E's that are identical. So by virtue of using that formula, you would say that the number of permutations is 10 factorial divided by 2 factorial divided by 2 divided by 3 factorial. Comes out to be 151,200. Now, it's fairly easy to understand what's going on there. If you've got these 10 letters in Bookkeeper, and you just scramble them all together, each one of those 10 letter rearrangements will have an O here and an O there. Well, if this is the first O in Bookkeeper and this is the second O, it's indistinguishable from putting the second O here and the first O here, all right? And you don't want to count those as separate rearrangements. The O's are the same. It doesn't matter where they fall in Bookkeeper. So you've got, if you just say 10 factorial, you've got a factor of 2 copies, if you will. Same thing with the K, and then with respect to the E. The E's, there are 6 different rearrangements of those 3 E's. So you need to, if you want to factor out those duplications, you have to take out 2, 2, and 6 for the O, the E, and the O, the K, and the E. So here's the last one. Combinations are a little different than permutations. They are the number of different combinations of indifferent objects selected R at a time. The rearrangements within a combination no one cares about. Okay? The way that you see it written is order is not important in combinations, whereas of course it's important in permutation. So if you just look at that formula, in things taken R at a time, you see it's the same thing as permutations, but it has an additional factor of R factorial, which takes all of the permutations out. So, for example, if you wanted to calculate the number of combinations of 4 things, 2 at a time, it's written as it's shown there. That's 4 factorial over the difference factorial all over the R factorial, if you will. That's 24 divided by 2 divided by 2, that's 6. Yeah? And if, again, we now take the 4 objects to be the letters A, B, C, and D, then there are the 6 2 at a time combinations of the 4 items, A, B, C, or D, just below. All right, well, one more view graph. I know we've gone through these extremely quickly. But this is an example to show you these definitions, permutation, in this case combination definitions, in action, in doing a very specific type of counting. Let me read the example to you. It says, in a club there are 7 women and 5 men. A committee of 3 women and 2 men are to be chosen. How many different possibilities are there? So the first thing that it says is there are not separate roles listed here for each committee member, meaning that within the committee there's no hierarchy, there's no order. All right, order is not important, and that drives you to calculate combinations rather than permutations. So what you want to do is find out how many groups of 3 women out of 7 are there, how many groups of 2 men out of 5 are there, multiply those two together, and by the fundamental rule of counting, that's the total number. So again, the number of groups of 3 women out of 7 is 7 things taken 3 at a time. 7 factorial divided by the difference factorial divided by 3 factorial. That turns out to be 35. Again, you'll be able to use your calculator if you like. I'll show you how to do that soon enough. And likewise, how many groups of men, of 2 men out of 5 can be selected. 5 things 2 at a time. 5 factorial over the difference factorial all over 2 factorial is 10. 35 times 10 is 350, and that's the answer. All right, yet another thing that really takes some practice to get good at. We'll revisit some of these in the mastery section, and again I'll repeat that what I'm interested in having you be able to do is identify when certain calculations require permutations, when they require combinations, do they involve order or do they not, and how to do these calculations like this, 7 things 3 at a time or 5 things 2 at a time. All right, very good. See you soon.